Hello and welcome to lesson 7.1. The usual sampling distributions. The usual way to gain information about a population characteristic is to select a sample from a population. However, we must note that the sample information we gather may differ somewhat from the population characteristic we are trying to measure. Further, the sample information may differ from sample to sample. This sample to sample variability poses a problem when we try to generalize our findings to the population. In order to do so, we must gain an understanding of this variable. What is a parameter? What is a statistic? How is one related to the other? The parameter is a description of the population, but a statistic is that measure of the sample. So if I was to say that our class has a GPA of a mean GPA of 4.1, if I was to only sample 3 people, I might get a mean GPA for them of 3.9. I might get a mean GPA of 4.25. I might sample another time, another 3 students, and get a mean GPA of 4.151. So I might be close to the true parameter for the mean GPA of the class, but I might not be right on it. So a statistic comes from a sample, but a parameter is the true value for that population that the statistic is trying to estimate. A numerical summary. Okay, so parameter and statistic, let's just talk about notation. For a proportion, which means a proportion of students with brown hair, let's say, normally these are things like colors or some non-numerical measurement, then we can just turn the percent or proportion of people into the number that we're talking about. Then that way we can make things numerical. So the proportion, the parameter is just a lowercase p, and the statistic is a p hat. This is for categorical data. Means and standard deviations, though, are for quantitative data. So we use mu for the parameter, or x bar for the statistic, and sigma for the parameter, and sx or s for the statistic. Vocabulary is very important. Confusing your notation will cause a loss of credit on the AP exam. Identify the population, the parameter, the sample, and the statistic. On Tuesday, the autofill coffee machine at the McHenry Starbucks filled medium, grande cups of coffee. They are supposed to fill an average of 16 ounces of coffee in the grande cup. Quality control inspectors visited the store and sampled 50 grande cups at random from the day's production. Those cups contained an average of 15.6 ounces of coffee. The population is all the grande cups of coffee at the McHenry Starbucks. The sample was the 50 grande cups taken at random from one day's production at the McHenry Starbucks. The parameter is mu. This is actually unknown. It's supposed to be 16. Okay. But our statistic is x bar, which is 15.6 ounces. Okay. So we don't know what the machine is truly filling to, but we got a statistic of 15.6 from our 50 cups. A Pew Internet Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% yes. 71% said yes. The population is all 12 to 17-year-olds in the U.S., and the sample was only the 1,102 12 to 17-year-olds. The parameter, p, is the true proportion of yes. We don't know what that is, but the statistic is p hat equals 0.71, the proportion of the sample that said yes. They have a cell phone. We can view a sample statistic as a random variable. That is, we have no way of predicting exactly what statistic value we will get from a sample, but given a population parameter, we know how those values will behave in repeated sampling. If we could find all the possible samples of a given size from a population, we could find the corresponding distribution of sample statistics. So what this is beginning to suggest is that we would know more about how much these samples vary if we were to take every single sample possible, and then we could lay them all out on a normal curve. They'd probably be normally distributed. And then we would know how likely ones like this are to get, okay? And we would maybe know more likely what the true parameter value is as well. Okay, so get a plate, a bag of M&Ms, and a cup. and you would be distributed a bag of M&Ms, a cup, and a plate to work on. Count all your green M&Ms. Count all of your M&Ms. My group's total green and my group's total M&Ms, and then my group's proportion of green. And then other groups' totals of green. So some groups had 25, 20, 31, and all these values of greens. And the other groups' totals of M&Ms. Going the same order around the room, I wrote down the M&M totals. The class total for green is 209, and the class total of M&Ms is 1082. Now I pooled all those values together because I considered them as all parts of the whole because they all came from the same mega bag of M&Ms. Okay, so the class, or the population, proportion of green was 0.193. Put the candies back in the cup. Shake. Take a sample of 25 pieces from your group's cup. Find your sample proportion of green M&Ms. So now we know how many greens are in the class. Now we're going to take samples. Is this sample proportion exactly equal to your group's population proportion? Why or why not? The sample is not always equal to the population proportion due to sampling variability. Do the sample 2 more times for a total of 3 sample proportions. Sample proportion 2, sample proportion 3. All that we're observing is that our proportions vary from the true proportion of green M&Ms we have in front of us. And true, each group has a different proportion of green M&Ms in front of them. However, among a group, their sample proportions are varying from the true proportion. Make a dot plot of the class's proportions. First, each group needs to share out to compare with the other groups to find the smallest proportions, so that was achieved, and the largest proportion, so we can make our number line. After we have a number line here, though, we go ahead and we start putting dots in. And then we have to figure that if there was many, many more groups of students, what this would look like, and it will start to approach a normal curve, and it will not be multimodal, okay? The way that this one started to sort of look, the way that it had quite a few dots and then 1 dot, then quite a few dots and 1 dot, and quite a few dots and 2, 1, 1, okay? Those would fill in that center area. Okay, what is sampling variability and why do we care? Sampling variability is the variability of a statistic in repeated sampling of the same size from the same population. Example, in the M&Ms activity, each trial had a different proportion of green, even though the proportion was constant. Okay, even though the true proportion of green was constant. So each group did not eat any M&Ms. They still had this golden proportion in front of them, but when they did their 3 sample proportions, they had different values than that true value of green. Okay. So in the M&Ms activity, each trial had a different proportion of green, even though P was constant. We need to be aware of the variability of our samples in order to estimate how close our sample is to the true population parameter. This distance between the statistic and the parameter is called the margin of error. What is the sampling distribution and why do we care? The sampling distribution describes all possible statistic values and how often they occur. It's normally a histogram or considered a density curve because it's a smooth curve that connects every possible value. We need to be aware of which statistics are common and which are unusual. Is there ever variability of the parameter? No. Why? The parameter is the true value of on the population. Consider our population as closed and frozen in time to truly understand that there is no variability of the population parameter. Okay, we use technology to simulate choosing 500 SRSs of size 20 from a population of 200 chips where half are red and half are blue. The dot plot shows the p-hat, the sample proportion of red chips for each of the 500 samples. So 500 times we took 20 chips from this distribution. So the true population distribution, the proportion of red is 0.5. When we took repeated samples of 20, we one time got 12 blue and 8 red. So the proportion of red is 8 out of 20, which is 0.4. Another time we got 9 blue and 11 red. So then the proportion of red was 11 out of 20, which is 0.55. So we take 0.40, put a dot, 0.55, put a dot, and we keep taking more and more and more samples and putting more and more dots here. Now, after we've taken 500 samples and put 500 dots here, we start to see this develop. There is one dot on the graph at 0.8. Explain what this value represents. This represents drawing 16 red chips out of 20. Once out of 500 SRSs this occurred. Would it be surprising to get a sample proportion of 7 out of 20, which is 0.35, or smaller in an SRS of size 20 when p equals 0.5? Justify your answer. No, it would not be surprising to get a proportion less than or equal to 0.35, which starts here and works down, because I estimate this occurring about 10% of the time in the approximate sampling distribution above. In a real AP question, that would be a little more easy to determine, that actual percent of the time. Is there convincing evidence that less than half of the chips in the bag are red? And explain your reasoning. So this is the proportion of chips that are red, about 50%, and then the bars compare this way. No, there's not convincing evidence that less than half the chips in the bag are red. The approximate sampling distribution is roughly centered at 0.5, with half the data left and half the data right of 0.5. Terminology matters. Don't say sample distribution when you mean sampling distribution. So let's be careful here. This is a sample distribution. This is a sampling distribution. So be very specific of that small change in wording, okay? All right. You will lose credit on free response questions for misusing statistical terms. Also avoid ambiguous statements like, when the sample sizes increases, the variability decreases. The variability of which distribution? Okay. All right. A father has 4 sons with heights 68, 71, 72, and 75 inches. Determine the sampling distribution of the sample mean x bar for sample sizes of size 2. Now, we can go ahead and take the 68 and 71 boy and get the mean, the 68 and 72 boy and get the mean, the 68 and 75 boy and get the mean. So then we did the first and second, the first and third, and the first and fourth boy. Now I need to do the second and third boy, and the second and fourth boy, and then the third and fourth boy. Then I've combined all the pairs of boys together. And I have this sampling distribution of sample mean. It is symmetric and unimodal and centered at 71.5. So it seems to lead us in this direction of thinking that maybe the overall mean of their 4 heights is 71.5. So let's just add it up. 68 plus 71 plus 72 plus 75 divided by 4 is 71.5. So the mean is centered at the true center of this distribution of heights. Okay. It is very difficult to make a sampling distribution in the real world because it requires knowing every individual's value and graphing the statistic for every sample of the same size possible. The sampling distribution is the ideal pattern if it's achievable. Let's go back to yesterday's ticket out the door, the poker chips. A bag contains 200 poker chips, 100 red and 100 blue. If each student takes an SRS of 20 chips and records a proportion of red chips, what is the difference between the distribution of the population, the distribution of the sample, and the sampling distribution? So the distribution of the population is just a little review, is the whole blue-red distribution here. The distribution of the sample is every individual sample that we took. And then the sampling distribution, or the approximate sampling distribution, because it's only 500 samples, is shown here. Okay. A deck of cards with aces and face cards removed so that only the cards 2 through 10 remain. What is the median of the deck of cards, and what is the range of the deck of cards? Okay, so then what I did is I had each student shuffle their partial deck, randomly select 5 cards, and note the median value for the cards and the range for the value for the cards, and do this 5 times total. So they listed out the median of their cards and the range of their cards. Remember, the range is the max minus the min. Have each student record the value on of the sample median on a dot plot from 2 to 10. Have each student record the values of the sample range on a dot plot from 1 to 8. So 2 to 10 and 1 to 8. Now, what do we notice about these dot plots? This one seems a little bit mound-shaped. This one seems a little bit skewed left. Put an arrow on the bottom of the axis for the population median, 6. And it does seem somewhat centered in our very short, small number of samples here. And put an arrow on the bottom of the axis pointing to the population range. Here's the range though. The population range is 8 because there are cards 2 through 10, and so there's a range of 8 present. But our sample range was not very good at telling us that. Okay, how does the population median compare to the mean of the approximate sampling distribution of sample median? This is the sampling distribution of sample median. Okay, sampling distribution, well, approximate sampling distribution, because I only did this like 50 times or so. It's only 50 data values of sample median, meaning that we over and over calculated our median. Okay. So let me go over that one more time. How does the population median compare to the mean of the approximate sampling distribution of sample median? Okay, so what that means is that the mean of this distribution and the true median are approximately the same. Okay. The mean is at approximately 6, and that is the true mean of the population. How does the population range compare to the mean of the approximate sampling distribution of sample range? The mean of this might be more like 6-ish or 6.5-ish, but the true population range is 8. So the population range is higher than the mean of the approximate sampling distribution of sample range. Sample range is an underestimate of the true population range. So over and over, we see a systematic underestimate of the true population range, because only these times did we actually estimate the true population range, because we truly needed present in our little sample of 5 cards, we needed a 2 and a 10 in there in order to get the range of 8. If there was anything else, not exactly a 2 and a 10, then we would have gotten a smaller range, and that happened much more often than getting the true range. So this is a systematic underestimate of the true range. A statistic used to estimate the population parameter is an unbiased estimator only if the mean of its sampling distribution is equal to the value of the parameter being estimated. So we really want the mean of the sampling distribution to be equal to the parameter that we're trying to estimate, okay? We don't want to have to stick with a max of the sampling distribution in order to estimate the true value of the parameter. Okay, so we're mean focused. All right, an example of an unbiased estimator is an estimator for center. Take the sampling distribution of sample means. The average should be close to the true mean. This does not mean that they are a perfect match, though. It just means that it's not, our sample estimates aren't consistently high or consistently lower than the population parameter. A statistic that is consistently higher or lower than the population parameter is a biased estimator. An example of a biased estimator is an estimate of spread. Take the sampling distributions of sample range. The possible sample ranges will have an average much less than the true range. Okay. If the sampling method, like convenience or some other method itself, is biased, then the sampling distribution will also be biased, regardless of its sampling, of it being a sample distribution of a measure of center. How can you reduce the variability of a statistic? You can take a larger sample, and by better designs, like a stratified random sample instead of an SRS. Okay, so up here we have 2 different sampling distributions, and the approximate sampling distribution of the sample proportion p hat from SRSs of size 100 and 1,000 are drawn from a population with proportion p equals 0.37 of people who have watched Survivor. So if I have a really large population that I'm pulling from, and if 37% of them have watched Survivor, the population proportion is 0.37. Then if I sample just 100 people, I might get a sample proportion as extreme as 0.25 that tells me that only 25% of people watch Survivor, or as extreme as 0.55, which tells me 55% of people watch Survivor, or any of these other outside smoke kind of values. But if I jack up that sample size to 1,000, then even my outside chance possibilities are much closer to 0.37, the true population proportion, than when I took a smaller sample size. So I have a lot less variability when I increase my sample size. Okay, what effect does the size of the population have on the variability of a statistic? It doesn't have much effect. Remember this fact: as samples get larger, variability is reduced. So sample gets larger, variability is pulled in. But we can never sample more than 10% of the population. Okay, so we can go this big as long as we have less than 10% of the population that we're sampling. Okay, so let's compare these three things to discuss the size of the population now. A truck of corn, or a silo, which is equal to 2 dump trucks of corn, or a sack, which is equal to 1/50th of a dump truck of corn. If we were to take a scoop of corn from each in a little scooper, if I took it from the truck, from the 2 truck size, or from the 1/50th of a truck size, as long as it's all mixed up really well, my sampling distribution of corn kernels would look no different from truck, silo, or sack. Okay? So what that means is that what effect does the size of the population have on the variability of a statistic? Not much. Okay? But what effect does a sample have? Great difference. If you can go 10 times bigger, you're going to get a little bit less variability. Okay? All right. So let's just add some more vocab words to this. What is the difference between accuracy and precision? Accurate means that we're heading for the bullseye. It's unbiased, it's not far off the true mark. Precise is low variability. That means how close the values are together. How does this relate to bias and variability? Bias means it's not accurate, but it still may be precise. Variability means it might be generally accurate, but it's not precise. What is the ideal estimator? Accurate and precise, low bias and low variability. Thanks for joining.